friends, happy final day of the 4C experience. I hope it's been a productive one. I just have a couple of reminders here for you. The PLC 15 is for Friday this week, and homework 9 has been going. Final celebration next Wednesday. So please make sure you have your time, your calendar marked, your time blocked out, a good place to go, and just be ready to knock it out and submit, be done. So that's what we'll do. Again, I was going to remind you, if you are on campus on the Tuesday prior, I will be hosting a review session in room 804 here on Aptos campus. If you are around and interested, that would be Tuesday from 10 to 1 here in room 804. So if you have last minute questions, you are free to use that. You are also free to fire an email and see how that goes. So otherwise, we are here at this is the final class session for our spring semester here. And so we will finish up a little bit of the radioactivity. We'll go through and do a little bit of review, take a look at a couple of example problems, and then we are going to sign off and call that a semester. So I'm going to finish up talking a little bit about radioactivity, as we were talking about that yesterday. So nuclei decaying, and we started off with a simple example of how to look at a parent nucleus and deduce the daughter nucleus. Certainly you could go in the reverse situation. Given the products of the reaction, you would try to figure out what the initial thing was. What's the word for that? Products. Given what given what's emitted, given the radiations, go figure out what it was that started out as. And so I mentioned the ways to think about how to look at the periodic table and deduce either what the daughter nucleus looked like, or daughter nucleus looks like, or what the parent nucleus was, based on where you are in the periodic table and what else has been emitted. So this is essentially like an algebraic equation with 3 unknowns in it. Okay? So there's what you start with, what nucleus you start with, what nucleus you end with, and then the emitted products. So it looks something along the lines of, I've been talking about the parent nucleus, right? This is what you start with. It becomes the, I'm going to call it the offspring nucleus, plus whatever the decay products are. So what happens here is that essentially, if you consider this as an algebraic equation, given 2, you're determining the third. So if I know what this is, and I know what these were, then all I got to do is figure out what this is. And that's kind of what the modality was that we went through in the previous class. Starting with a known nucleus, and then watching it decay via these 3 methods. What is it that is then produced? Certainly you could look at it from a couple of different example routes. Knowing this and knowing this, what came out, right? That's also something that would be doable. And of course, knowing this and this, what was it that we started with, all right? So thinking of this as an algebraic equation can be kind of useful in the sense that you have these 3 things that you're looking for. You would need to know 2 of them in order to figure out what the third one is. We talked about the decay modes, alpha, beta plus, and minus, which fall under 1, and then the gamma. So here
we had the helium nucleus. Here we have the X-ray, the high energy X-ray, which is just electromagnetic radiation. And then here we have electrons and anti-electrons called the positrons. So, just remind everybody of this. This is a positron emitted. The positron emitted typically comes with a neutrino on the end of it, and I believe, put that in the homework. When you look at the reaction, the neutrino is in there. When it's the electron emitted, it's the anti-neutrino, so it should be a nu with a bar on it. And then the gamma is just EM radiation. I was finishing last class, if I remember correctly, I was finishing last class talking about what happens if uranium-238 decays via gamma. Just to finish off that discussion, because I think I was probably kind of getting there at the very end of the class. So, if a nucleus is in an excited state, just in exactly in the same way that an electron could be either in its ground state or in its excited state, or in an upper level excited state. We also can draw energy levels for nuclei. The ladder for a nucleus is going to have much larger spacings than it would have for an electron in an atom. So, as an example, for the laser discussion, I drew a couple of energy level diagrams for helium and neon. And those are ones, just to remind you, they looked kind of like this. There would be well, I guess I didn't have the sides to it, so it didn't really look like a ladder. But essentially, it's that idea of the staircase, right? The low state here is the ground state, and then there's a state here and here and here, and then there's one here and here, and there's here and here, right? And you're looking at these different states. This would be the ground state number 1, you would typically call that. So this would be 2, 3, 4, and 5. We did the same thing in the hydrogen atom. We did the same thing with the laser discussion. We can do the same thing with nuclei. It's just that the spacing is much, much larger. So if a nucleus is up here, even in its first excited state, by the way, just to let you know, the first excited state is the first state above the ground level, above ground state. Ground state, I usually call that 1. The reason is, when you look at the infinite square well, when you look at the Bohr model, all of those n's are equal to 1. And so you either can call that the ground state is E1, or you can call it E0 and then have E1 be that. So the naming of the first excited state means n equals 2. So I believe on the homework, I've had a few questions about what does it mean when it's in the fourth excited state, or the first excited state and the third excited state. Well, that means this would be the first excited state, n equals 2. And then the third excited state would be not 3, but 4. So think about that as you're going along. Here's the ground state down here, n equals 1. And if a nucleus undergoes a transition from an excited state to a ground state, it emits a gamma. Just as a photon would be emitted when an electron dropped from, say, here to here. Right? A photon comes out, and we say, oh, we can figure out the energy of that photon because we know the difference in the electron energy levels, and therefore the wavelength here is going to be characteristic to that energy difference between those levels. If the nucleus goes from 2 to 1 and emits a photon out, that energy difference is very large, typically. We would denote the excited state nucleus by having a star on it. So, in the way that I was writing it last time, let's get this. In the way I was writing it last time, 23892, like this would be the excited state of that nucleus. The star means it's got a little bit extra energy. It then would decay. into exactly the same thing. Let's see if that fits on there. Oh, good. It would decay into exactly the same thing because the gamma carries no electrons, protons, neutrons, carries nothing with it except just the energy that is emitted via the transition of the nucleus from the excited state to the ground state. And so the reaction would be written this way, and this would be maybe the picture that you can think of as you're thinking about undergoing this process. Okay. All of the same mentality holds. In other words, if we measured either the energy of that gamma photon or the wavelength of that gamma photon, and then we could find the energy of the gamma photon, that would be the same as the energy difference in these energy levels. And you'd find that to be horrendously large compared to what we're used to here with the electrons, where you're talking about something on the order of typically less than 10 EVs. This would be possibly thousands or tens of thousands of electron volts. All right, so this would still be Hc over lambda to find the energy, and that energy of the gamma would still correspond to the energy difference in the levels here for the nucleus. Okay, so that delta E. Again, we need a negative sign just to make the balance right, but ultimately, if you think magnitude of this and magnitude of that, it'll work out. They should be the same. Okay, so this is where we had left off last time. Just to kick things off again, I'll just remind you, this is it's like a game of what's that game where you're moving? It's not like Sheets and Ladders, but it's something like that, or maybe it's Sorry or something. This is to the right two spaces. No, that's wrong. That's totally wrong. That is totally wrong. It's to the left two spaces. If I consider the product, in other words, I consider the offspring nucleus here, from the parent, if it decays via alpha, the offspring is back two spaces. I guess I don't necessarily want to say to the left, because if it's something like this, it might wrap around, but with repeating boundary conditions such that if you go this way, then you pop up over here and you're still going left, it decreases your atomic number by 2. Let me put it that way. This decreases it by 1, so this would be to the left 1 space. This one is to the right 1 space, and this is going to change. Okay, so basically I'm charting out here what happens to the offspring nucleus. The offspring nucleus compared to the parent. So the parent, as I said last time, if that's something like a uranium, then the offspring is going back 2 spaces. If it's alpha, it's going back 1 space. If it's beta positive, it's going forward 1 space if it's beta negative, and there's no change whatsoever if you are going to gamma. The gamma reaction is that. So you can probably see, the way I typically remember this is that the direction on the periodic table is opposite what these decays are. So if it's beta positive, you lose 1. If it's beta negative, you gain 1. So it's the opposite of what you think. In that sense, at least that's how I remember it. All right, I got one thing here that I wanted left over to talk about here. Now, we talked about beta positive decay and we talked about beta negative decay last time in terms of what are the neutrons and protons doing relative to one another. So in this case, this is the beta positive decay, conserves charge. So this is a proton which is decaying into a neutron, but I have to have charge conservation, and that means I have to have something in here that's positive charge on the right side in order to balance the positive charge that I had on the left side. So that charge has to show up somewhere. It cannot go away. This one is the one with the neutrino. This is the one in which the reaction is the opposite and goes this way. Anti-neutrino. Now, I want to just take a quick look at these two things. Notice that they are they opposites of one another? Notice that they're opposites of one another. In other words, if I treated this as an algebraic equation, once again, all right, then I could look at this and say, all right, if I were supposedly to solve for the neutron in this upper reaction here, if I were to solve for the neutron, I would say, oh, neutron, that's going to become a proton on this side, so I've got the proton already here, but now I have to subtract off the positron, and I have to subtract off the neutrino, right? Like that. So, if I compare that to this, what have we done? What we've done is we've taken away a positron. That's kind of like adding an electron. Because when I take away a particle, that's like adding its antiparticle. So I can change this over by saying, all right, if I consider the antiparticle of these, then I can flip the algebraic sign. All right, so the antiparticle to the anti-electron is just the electron. So I could change that into an electron. I could change this, the antiparticle to the neutrino is the anti-neutrino. But when I do that, I have to change the algebraic sign, and that means I change both of these minuses to pluses. If I just leave these two the way they are, then you'll notice I'm recovering this. I say that because there is one more modality of decay that I wanted to talk about, and it's known as electron capture. So it's a situation in which a nucleus has basically reached out and grabbed one of the inner shell electrons. This is just called EC. So that the nucleus has basically swallowed up one of the electrons that's nearby. You can imagine this in the sense of drawing a picture that would look something like this. I would have the nucleus here. If I just looked at, we talked about the Bohr model, so let's just imagine that I had a Bohr model type atom here. So I have a nucleus, maybe this is something like carbon or something, okay? So carbon has 6 protons in it. It'll have 6 electrons going around it, and we can talk about the 2 electrons that are in the 1s shell, and the 2 electrons in the 2s shell, which should be out here, and then the 2, how many do we have? Or the 2 electrons that would be in one of the 2p shells. So let's incorrectly, okay, this is incorrect, but it does okay as a mental picture. If I label this something like the 1s, the 2s, and the 2p, then it's funny for me to look at something like that, so I can't imagine what it's like for you. But nonetheless, it looks like a big target, and we're going to shoot the bullseye here. I've got 2 electrons in the 1s. Well, I've got 2 in each of them, okay? So I've got an electron here, 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 okay? So they're doing whatever they're doing, right? These are electrons which have standing wave orbits. They're in a stationary state. They're making their probability waves, however they're doing it. We're going backwards a little bit, thinking of it in this way, because the modern way of thinking is the Schrodinger and the probability wave style. The Bohr model is a bit of a, it's like, what do you want to say? I mean, it's kind of like using stone tablets when we have iPad tablets or whatever tablets. It's like using stone ones instead of regular ones. What's going to happen is this nucleus is going to reach out and swallow up one of the electrons in the 1s. Suppose that it reaches out and grabs this one. So that now there are only 5 electrons left. What's going to happen then is that you're going to undergo a kind of a forced reaction. One that is kind of like this. Okay? Now, recall, this is a carbon atom, so it has 6 pluses and 6 minuses, so it is electrically neutral to start with. And since we cannot suddenly create electric charge out of nothing, and we cannot just throw electric charge away so it becomes nothing, right? If you look at these things, they're charge conserving. The plus sign, the plus charge here migrates to the plus charge on this side. The zero charge here is balanced by a plus and a minus on this side. So electric charge is conserved. It is a conserved quantity, just like energy, or energy slash mass. And just like protons plus neutrons, okay, it is a conserved number. So I cannot just suddenly end up with a positive or negative atom here. It has to be charge neutral, because it started charge neutral, so it's got to end charge neutral. If I've lost an electron, then ultimately this must be a situation in which I'm losing a proton also. Alright, so can you see that it's something kind of like this? It's a proton. I'm losing a proton. A proton's going into something else, but it's not doing this. It's doing something a little bit different. Well, if I apply that reasoning up there, in which I can think of adding and subtracting particles, but then changing their algebraic signs in order to make them the antiparticle of what I had, or the anti-particle, then I can do a quick analysis of this here. What that looks like would be a proton has essentially swallowed up an electron here. There's a situation where a proton plus electron has become a neutron. Okay, like that. And you say, well, which one of those is this kind of like? Well, it's kind of like this one. But the electrons over on the left side, that would be okay. If I took this equation here, like I did up here, and instead of, no, I didn't, I solved for the neutron. So instead of solving for the neutron, what if I just subtracted the positron off this side and put it on that side? If I do that, right, then if I go minus positron on this side, I got to do minus positron on this side. Okay, that means what I'm going to end up with here is proton minus positron going to neutron plus neutrino. And remember, I can flip the sign if I make it the antiparticle. So now I'm talking about looking something like this. Okay, so I'm going to erase that and put it down here. Now I'm talking about doing this. If I'm going to change the algebraic sign of this thing, I'm going to change the particle into the antiparticle. Well, this is already an antiparticle, so that means I'm flipping it back into its regular particle. So now I'm going to do, whoops, N naught. No. N naught plus neutrino. Okay. So this is the electron capture algebra, if you like. This is the reaction that's called electron capture. And that's a situation where the electron has been just, like I said, swallowed up by the nucleus and then has changed into a neutron. Now, I was saying in the last class, and rather vehemently so, if I may say, that I would really like it if you did not think of the neutron as a bound state proton-electron pair. Like I said, they're not. So you might say, well, what happens to the electron in this case? Where does it go? Well, that's a good question. But ultimately, it's helping the proton become a neutron. And there's a lot more bit of technicalities to it like this. You can certainly think of it as the case of instead of subtracting a positron on both sides, I'm adding an electron on both sides. So really, if I wanted to take a slightly different approach to this first equation here, what I might be able to say is the proton grabs an electron, right, and becomes a neutron plus a positron plus an electron plus a neutrino. And therefore, these two things here are going to disappear. They're going to go away. All right? And you're going to be left with essentially a neutron and a neutrino, probably with a little bit of leftover energy. But that energy helped make this reaction happen. So you can kind of think of it that way too. It's not so important which way you think of it. The important part that I want to get across to you is that you can play with these equations and their algebraic signs as long as you flip the particle to being the antiparticle, or the antiparticle to being the particle, as it is in this case here. Therefore, electron capture is basically beta positive decay. Alrighty? That's what the ultimate ending point of that discussion is going to be. All right. So, with that being said, there are many other things that we can certainly do with the radioactivity portion. I mentioned in the last class that part of how the electron or the positron gets produced is due to energy which kind of makes the mass for you. Well, that's exactly what the radioactivity processes is based on. It's based on losing a little bit of mass and causing that little bit of mass to become energy, so that the energy released from a radioactive decay is because everything that you have left over now weighs less than what you started with. The parent nucleus is heavy. The offspring nucleus plus the decay products does not weigh the same amount as the parent. It weighs less. That lowering of the mass turns into the energy that we get out of that or that is released by that radioactive event. Okay. And so you can calculate this. You can calculate how much energy do you expect to be released by a radioactive event. So I'm not really going to go into any more than that, other than just to put that out there, that this is something that is calculatable and that we can predict. So the reason I wanted to say that was because we utilize this energy release for different purposes. Okay, so one of the things we utilize it for is blowing stuff up and just having it to be an uncontrolled reaction, uncontrolled chain reaction. But if we want to talk something about a little bit more practical, let's talk about what happens when we can make this energy a sustained release. In other words, we can have a nuclear chain reaction, but we can moderate the chain reaction in a way such that it, instead of increasing without limit, we keep it at a reasonably constant level. And when we keep it at a reasonably constant level, that means we get a reasonably constant power output, and then we have useful energy that we can supply to people. And in fact, I will take you back to the very beginning of this, not this, but of this field. The radioactive field and the understanding that we have the ability to control radioactivity and the energy it produces started in the early 1930s. And it started with someone realizing the energy that's coming out of radioactive decay is something that we can use. And at that point, this person, one of their first thoughts was, we've just solved humanity's energy problems. We have this source of essentially unlimited energy that everybody in the world could use. And it didn't quite work out that way ultimately to this point. But you know what? Fingers crossed. Maybe we still have a chance. We don't know. Let's get rid of this. All right. So I thought what we could do here is talk a little bit about what some topics are that would be showing up on the final. So I'm going to go ahead and say this is that discussion. That's the end of our material. So from here, it's just going to be review. So this marks a transitional point in our class, and this is the end of talking about material in 4C. So hopefully you enjoyed it. I know I did. Because gosh, there's nothing better than physics. Well, there's a few things that are better than physics, but it's up there. Let me put it that way. It's definitely the best science, and I'm not just saying that. It's actually true. So let's take a look. What topics are we going to find showing up? Well, like I said, the final is essentially a two-legged animal. It's partly all of the stuff since Celebration 2, and it's partly all of the stuff prior to Celebration 2. Therefore, we have to think about what kind of topics are we dealing with in both of those regions. Let's take a look. So prior to Celebration 2, this would be the situation where we're looking at the beginning of the class all the way through the first celebration, all the way through to the second celebration, that chunk of material. We're looking at the highlights of this, okay? So, laws of thermodynamics. To start, back at the very beginning of the class, the very first day when I started talking about, well, these are some of the laws we're going to be dealing with. Laws of thermodynamics. I talked about all four of them, but we really only going to concentrate on numbers 1 and 2. As things by which we want to guide our thinking, by which we want to do calculations, by which we draw and think about what's happening and use reasoning. We're going to use these two laws to do those. And 0 and 3 are essentially foundational. So all of our work for this class came from 1 and 2. And if you remember, law 1 is essentially energy conservation. And law 2 is what effectively for us turns into the law of increase of entropy, but really isn't quite that, and we talked a bit about that. But the practical scheme, what do we end up with from law 2? Basically, we end up with the idea that either you can think of it in the Clausius sense, that heat does not flow backwards. Heat flows from a hotter to a cooler body. And unless we force it to do the opposite, it's going to spontaneously always go hot to cold. For me, that's a pretty easy way to think about what's going on with law 2. The Carnot interpretation and the Kelvin interpretation of law 2, in the sense that we looked at heat engines, right, and saying that, well, there's no such engine that takes heat in and gives work out. We showed those two to be equivalent. The Clausius interpretation of hot to cold heat flow and the Carnot interpretation of no 100% perfect engines. In other words, heat in 100% of that to work out. We showed that those were the same. Ultimately, through the work of Clausius, the thing that law 2 turns into for us is the law of increase of entropy. And notwithstanding perfectly reversible cycles, which, by the way, was mostly what we concentrated on, everything that's going to be spontaneous or irreversible is going to suffer an increase in entropy. The only way in which you don't suffer an increase in entropy, and that is to say entropy stays constant and has no change to it, is if you have a perfectly reversible cycle. All right? So everything else is going to suffer an increase in entropy. The energy conservation we talked about involved a couple of different things. It talked about heat transfers and how did the heat transfer and what effect did the heat transfer into, as well as phase changes in that, right? So heat transfer sometimes causes an increase in the temperature. It sometimes causes, or I really should say change in the temperature. And sometimes it doesn't cause a change in the temperature. It causes a change in the phase of the material. So we talked about, pursuant to law 1 here, we talked about the specific heat, or what I call the sensible heat. Which is the one that results in a change in the temperature of the material. Or it turns into a latent, which means hidden, heat transfer, which results in no temperature change, and that's why we call it hidden, because you cannot see the effects of the heat transfer on a thermometer. The hidden heat transfer involves a, say, boiling, or a melting, or a condensing, or a freezing, or something like this. Okay, so the change that happens here is the change in the phase of the material. Now, that doesn't mean the entire thing does that. It just means that at least some portion of it is going to do that, as long as you've reached the phase change temperature. Okay? So, at the phase change temperature, which we know for water would be 0 centigrade or 100 centigrade, we would end up starting to freeze or boil water. Some will, maybe all of it will, but just something's going to happen there. But the temperature will remain constant. One other part to this turned into how does the heat get there? So for this, we answered it with the questions of heat flowing via conduction, convection, and radiation. All right. We came back to radiation because we talked about the emission of thermal radiation as a black body effect. And the black body effect eventually led to a quantum mechanical description of the oscillators which emitted the radiation, and then also of the radiation itself. So the radiation here is definitely the more important, but if I picked two, then I would say the two more important ones for us in this class are probably the conduction and radiation in terms of calculation. But I do want you to think about convection at least in a conceptual way. What happens in convection? What happens in convection is that you talk about the temperature of the say warm body in a cooler atmosphere as decreasing exponentially. So, excuse me, I'm trying to sneeze here and it's not working. All right. Newton's law of cooling is related to this convection. That's the idea that things go by and say something like e to the minus something, right? It decays via time, e to the minus kt, for example. Okay, whereas conduction is a direct contact type of thing, so air is directly contacting our skin, so we transfer heat from our skin into the air because it's in direct contact, and we also radiate because everything above zero temperature radiates. Excuse me. So here in these heat transfers, the radiation character is a T to the fourth type of character. Yeah, there are other things involved like the surface area and all that stuff, but ultimately the character of the radiation is captured by its T to the fourth dependence. Whereas over here in conduction, I got to be a little careful. Or we all have to be a little careful, because if I have to, so do you. This delta T is not a change, but it's rather a difference. I'd much prefer to write this as the gradient, but I'm told that I can't assume knowledge of the gradient prior. So we're going to use the difference in temperature, and we're going to divide by the thickness through which the heat flows. In other words, the separation in space between the two temperatures. Right? For that, go back to the glass example I did, where we had a hot temperature out here, we had a cold temperature out here, and we separated them by a pane of glass. So the delta T is not a change, it's a difference. We're assuming that these temperatures are not changing significantly, and the heat is flowing through the glass or through whatever this material is, and it has a length of L, or I should say a width, a thickness of L, such that the conduction rate is partly due to that. Okay. So heat going in and out and back and forth, kind of all through that. Now, I mentioned early on in this class that we were going to use the ideal gas as a backdrop to investigating the consequences of not just the laws, but also the heats that are transferring. So from the perspective of the application of this to an ideal gas, we have the ideal gas model in which PV was equal to nRT. And so when the heat flowed in, we were able to look at differences in the pressures and the volumes as a result of that. and therefore we were able to plot the pressure as a function of volume while we were looking at the temperature. So that led to PV diagrams that look like this. And remember that on these PV diagrams are hidden the temperatures, and they are hidden in these curves. Right? These are curves of constant increasing temperature. We'll label it that way. All right? So in looking at how does an ideal gas transition from one point on this PV diagram to another, we came up with 4 processes by which we could do that. And they were all kind of designed with something in mind. We had one in which there was no heat transferred at all. We had one in which there was no work done by the environment. We had one in which there was no no change in the temperature of the substance, right? And then we had one that was constant in pressure, like no change in the pressure of the ideal gas. So we have these 4 processes. This is a great number, the number 4, because when we get to optics, remember we've got the 4 questions. So we've got the 4 processes, we've got 4 questions, we've got 4 everythings. It's great. So 4 processes which we came up with, constant P, constant V, constant T, and Q equals 0. Like so. And we investigated the work done on the gas, the work done by the gas, the heat transfer to the gas, and things like that, by considering a cylinder and a piston and making drawings of what we think is happening. Okay, so a gas inside a piston and a cylinder, we could do different things with it. We could lock the piston in place. We could put a flame underneath it. We could put ice underneath it. We could cover it with insulation so that no heat could escape. All sorts of things. Okay, so knowing how those processes look on a PV graph and what kind of things you'd physically be doing to a piston and a cylinder in order to make those changes. Remember to go back and review. Okay, if it's constant volume, that means I've locked the piston and it can't move, and therefore there can't be any work done because I've got no volume changes. Just remembering the thinking that goes behind some of these things. Remembering that the work done is the area underneath the PV graph. Okay, and why that is. How to get it. Thinking through this type of thing. Gosh, there was one other thing I wanted to talk about, but I cannot remember what it was. Well, anyways, we then also, as a result of it was cycles. We talked about cycles. We talked about starting at one point and taking the gas through different points on the PV diagram via different processes and returning to the initial point. And therefore, we then talked about the cycle of all of those processes put together. And we talked about the work done by that cycle. And we talked about the changes in pressure and temperature and what that meant in terms of heats transferred and work done and things like that. So we came up with our first law. We applied our first law to this and came up with the consequences. So, of course, our first law being that the change in internal energy is Q plus W. So our first law is that, and we applied that to the system of the ideal gas and looked to see what happened. The second law was also the increase in entropy law, and that came in by looking at, okay, if I take the ideal gas through different situations, what is the change in the entropy looking like? And the change in the entropy can then be calculated as adding up all the little bits of heat that get transferred at a particular temperature. All right? So these two are kind of the manifestations of the laws 1 and 2 as applied to all of this type of thing. All right. So our thermodynamics looks something like that. When considering what is a reasonable thing to study for something like this, go back and think about, okay, well, I really like laws. So I'm going to think about how to ask you to demonstrate what you can do when you apply laws to situations. So thinking about how do laws apply to the ideal gas, how do we figure out what the consequences of this process are going to be? When I increase the pressure, what does that mean? Am I doing work? What heat's getting transferred? Is the gas doing work? What's the entropy look like? If the volume's increasing, if the temperature's changing, all of these things are kind of going along, and you're looking at the changes in the states of the ideal gas on a PV diagram, and then you're thinking about how does the heat and work transfer to making the entropy change and making an efficiency of the engine. Right. So if I take it through a process, remember we talked about an engine, the Carnot engine, I guess I could say here. But essentially the heat engines of any type worked something like this. Oops. In which I have a hot reservoir, a cold reservoir, and I have some type of piston cylinder, and I'm working that gas around based on the heat that I'm putting in, the heat that I'm dropping out, and hopefully it's ending up doing some net work for me. Thinking about the Carnot efficiency, and then thinking about regular efficiency as it relates to the entropy, gives us a way to figure out how big the QC is going to be in these cases, right? Because we know part of the argument is you can't make QC equal to 0 in these cases. That's part of Carnot's reasoning. All right, so think about the high points of this, and don't get too caught up in minutia of things like. For example, memorizing an equation about if there's heat transfer, how do I find the final temperature? Just set the thing up. Use the energy conservation, right? I would much rather see you showing how you think about the big ideas here rather than, and then maybe not going all the way through with it rather than trying to show exactly how you solved for this thing. Okay, so in a mentality situation about going into this, think about how to show and communicate your knowledge of take these physics ideas and apply them. That's what I want to see, and I'm not so concerned about, well, did you absolutely make sure that when you took this term over here, you changed the sign and then divided by m on both sides, right? That the math rules, right? That's for a different situation. I want to talk about the physics part of things. Okay. So that was kind of prior to celebration 1. Prior to celebration 2, we talked about optics and went through the high points, right? The high points from thermo included PV diagrams and piston diagrams and energy bar diagrams and things like that. So definitely practice those things. Get reacquainted with drawing the diagrams, because for me, that's a lot of how you communicate the physics to someone else, for example, me. we talked about optics. Now, the main thing in optics was initially with the ray model, we talked about ray diagrams, right? So we had these kind of three models of light. The ray optics one, in which we talked about how light travels in a beam. And that means you want to think about ray diagrams for lenses and mirrors. And then we have very little actual algebra to do here. We have the thin lens or the thin mirror equation, and we have the magnification. And that's pretty much it. So as long as you're, and we also have Snell's law. But as long as you're thinking about, looking at the ray diagram, understanding the principles of what the focus point is, what the center point does, how do the rays travel, what do I expect, where do I find the images, all that type of thing. And likewise with Snell's law and the refraction, how does a light beam refract into here, what happens when it hits this material, does it refract out, does it bounce in, all of these types of things. They're all encompassed by basically just these couple things. Knowing how to apply them and how to use them is the main point here. Okay, so we talked about the rays. We talked about the waves. The wave model. We found out that, in fact, the ray model is not 100% sufficient. So we had to talk about interference. And we also had to talk about diffraction. Now, interference is the superposition of two light waves, whereas diffraction is the superposition of thousands of light waves. Well, just more than two, right? Could be hundreds. Let's say between 3 and 1 million, right? I mean, when we talked about the single slit, we were thinking about 3 wave interference, 4 wave interference, 5 wave interference. So it's just greater than 2, really. And then when we thought about diffraction gratings, that number went up to thousands, right, ultimately. Interference, we know that there are 3 ways to achieve interference between these 2 waves. Path length difference, which I'll just abbreviate PLD, the path length difference, which we looked at the double slit as kind of the benchmark for that. We looked at wavelength reduction and what happens to the wavelength in a material. And we also looked at reflection phase shifts. So all 3 of these were present when we analyzed thin films. The path length difference showed up only in the double slit. The wavelength reduction shows up only when you have 2 light waves and one goes through a glass block and then they interfere after it emerges. Reflection phase shift shows up when you, for example, have light shining on a pond. I gave you an example of a radio transmitter or something like that. And one signal goes straight and one signal bounces off a lake and goes here. So that would be a reflection phase shift, as well as a path length difference, in fact. So thinking about how to quantify those and then bring them all together in a thin film setting. Diffraction talks about single slits and apertures. We talked about the Rayleigh criterion for distinguishing between 2 objects that are far away via diffraction. Just knowing what the patterns look like. Okay, what's the difference between the patterns? What does a grating look like? Gosh, what else did we do in that? I think that was pretty much it. You know, again, think of the high points. Okay, think of the high points. Snell's law is obviously a big thing here. How interference happens is obviously a big thing here. We talked about interference between waves and interference between multiple waves, which is just what we call diffraction. And then after that, we've been into the modern physics part of the class. So since then, we've done modern, which started with special relativity. And thinking about how clocks look, how lengths look, what happens on the space-time diagrams, interpreting the space-time diagrams, right? So, ST diagrams. Looking at what those look like and looking at the order of events. When things are simultaneous, how do we figure that out, etc., etc. So looking at the space-time diagrams along with time and space differences, right? We would call this time dilation and length contraction. After that, we started looking at the third model of light, which is the photon model, and we started with the photoelectric effect. So beginning with photons, we looked at the photoelectric effect, PE effect. We looked at Compton scattering. And after those two, we moved into looking a little bit about the Bohr model of hydrogen, looking at the composition and the types of light that's involved. How does the atom, in a very introductory way, how does the atom emit light or absorb light? Okay, we revisited some black body radiation at that point. It wasn't huge, but we just kind of linked back to the radiation that we had talked about in the thermo part of the class. We looked at the Bohr model, and we have kind of just finished looking at the sketching of wave functions and the application of the Schrodinger equation to different potentials. But I want to reiterate that I'm not going to ask you to solve the Schrodinger equation for different potentials, but as in the homework, I have a couple of situations where I'm asking you to sketch out what does the wave function look like for these different types of potentials, but not solve them mathematically. Just as in the special relativity portion here, we're going to look at the space-time diagrams. I don't ask you to draw them, but I do ask you to look at the ones I'm going to give you and interpret what they are telling us. How do you see that this is contracted? How do you see that these events are happening simultaneously, etc., etc.? Okay, so there's a difference in thinking about these things. We don't need to go through and know how to do these things. I did that one example for you so that we could have a basic starting point for what do we think the wave function might look like in the n equals 4 state. And now, if I make this change to the potential, how does that change this wave function? So the reason I did the solving of the Schrodinger equation was to give us the starting point of what wave functions look like. So we use those to start, and then we modify those wave functions in order to fit the new potentials. Let's see, last bit we talked a bit. Here we talked about lasers, and we talked about radioactivity. And that's that, lasers and radioactivity. And so that is basically the sum total of the course, more or less. Well, mostly less, because we spent a lot of time, as it turns out. Anyways, so that's about all I have to say for today. As I said previously, I appreciate your attention and your hard work in this class. And I do hope that you have felt like you've gotten something out of it. one of my goals is to help you really develop that logical reasoning and that communication of that reasoning. So again, when you're thinking about what do I need to study, also go back and think more about how am I going to communicate this stuff that I've spent all this time learning and trying to review and practice and ultimately trying to understand this material. How do I take that and then put it into a form that is understandable by someone else? Okay? In that sense, what I've been doing all semester is basically that process. I've been trying to take how I think about something and make it available to you. And hopefully it's in a way that you can look at it and say, okay, I think I understand how this is going. But ultimately, your understanding of the material happens when you put yourself into that position of trying to say, okay, how do I want to talk about how I understand this? Okay? Thinking about not just in some sense mastering the material, that's fine. But you can master all the material you want. If you can't tell other people about it, nobody knows. So please also think about how is it that you are communicating the material to me. Randomly putting different parts of things that go this way and this way and this way force me to try and follow how you're going through it. Try to think about organization, right? As you go through your solutions, organize it. Is it legible? Does it make sense how my logic progresses? Is it something whereby I'm using physics in every step and kind of explaining how I'm doing that? All right. Please do, when you look at the final, please do check in on what the wording of the question is, because there have been multiple times this class in which I've had to not give as good of a grade as I thought, because unfortunately the thing that got answered was not the question I was asking. So there was a turn, and all of a sudden we're talking about this other question over here, whereas I wanted to answer this one over here. So please make sure that you're trying to address what the question is asking. And ultimately, I will put this out there. Should you run short on time, please try to answer everything, or at least get something down for everything, okay? Because otherwise it's a standard no problem for me if I don't have any work for a problem. That's pretty well. Or you could go ahead and do that. That makes my job a lot easier. So thanks in advance. But think about how to put some physics down for everything. Should you manage to complete some to your satisfaction, that's great. But think about how to manage your time. There was one other piece that I wanted to mention because of Celebration 2. Part of it is this. When I ask a question, please don't skip over things like explain your reasoning. Take time to do that, because that's a big thing that I'm looking for. You might be able to solve all the math for it. That's great. I'd actually take away some of that time. If you can set up the math and kind of show where you would go, rather than algebraically putting the time into solving the algebra, put the time into writing out an explanation as to what's happening so that you communicate the physics to me. And that ultimately is going to be very, very helpful. So anyways, with those tips and those topics for review, I'm going to sign off for today and therefore for this class. And I thank you again for your attending and your hard work, and I wish you good luck. And since I know very few of you, should you see me walking around and say, oh, that's the guy I spent looking at 15 weeks on a screen, but he couldn't see me, please come and introduce yourself. I certainly would be happy to meet you and know where things go. So good luck to you. Stay strong. Review, study, and think about how to communicate your physics. And with that being said, I hope the rest of your finals go well, and I hope that you enjoy a well-deserved summer break. Alrighty, that's it. Then all I can say is thanks. See you later.